So for number 1 here, basically we're just going to be taking a simple square root. The way that we learned to do that in class was to break down the square root into smaller numbers by division. So let's go ahead and do that. We're going to say we have 150 x squared and of course y squared. So I like to separate the variables and numbers first. The 150 can be separated into 15 times 10. And then the 15 can be separated into 3 times 5. And the 10 can be separated into 5 times 2. And squared is just x, and y squared is y. So we have 3, 5, 5, 2, x, y. And basically, what a square root is you're looking for groups of two things that match. So we have 5 times 5. We can take a 5 out for that pair. X times x, we can take an x out for that pair. And y times y, so we can take a y out for that pair. And so on the outside of the square root now we have 5xy. And on the inside we have 6. And that's as simple as it gets there. Okay, so that's taking square roots. Look at another one here. This is a cube root. You'll notice that there's a negative underneath of the radical. Now, if you're ever dealing with a square root, that makes an imaginary number, which we'll talk about later in this video. However, when you're dealing with cube roots, it is okay to have a negative under the radical. So in other words, it's not imaginary. That's what I mean by it's being okay. But what we do anytime your root is an odd root, if you have a negative underneath, what we're going to do is we're just going to start first by taking that negative out. Put it out here. And that actually makes double negative on the outside, which cancels to make positive 2. In this case. Letters in that order there, but it doesn't matter. And then after that, we're going to handle this pretty much in a very similar fashion to what we did before. So let's go ahead and break this thing up as much as we can here. We have 448. We have x to the 7th. We have z to the 7th. And y. Alright, so the number is going to make us work a little bit here. I know 4 goes into that. 1, 1, 2. We know 4 breaks apart. 112. That's 56 times 2. 56 is 8 times 7. And then 8 is 2 times 2. So we have 1, 2, 3, 4, 5. 6 2's in there and a 7. And then we have 7 x's, 7 z's, and a y. So let's go ahead and so I've got 6 2's and a 7. I've got 7 x's. And I've got 7 z's. And then a y. Alright, and once again we're dealing with a cube root, so I'm going to put a 3 here. And that means I'm looking for groups of 3 things that match. So here we have 3 2's. For every group of 3 we can put one on the outside. Here's another group of 3. 3 x's there, so I can put an x on the outside. Another group of 3 x's, so I can put another x on the outside. and so on. Make my z's more like z's and my 2's look more like 2's. Put a line through my z's so we know that those are z's and not 2's. I think I put too many z's in there. Looking at it, I put 8 z's. There's only supposed to be 7, so I'll erase 1. All right. So now on the outside of my radical here, I've got 3 2's. You multiply those 3 2's together, you end up with 8. We have 2 x's, so that makes x squared. 2 z's, so that makes z squared. And then underneath of the cube root, we have a 7, an x, a z, and a y. There's that. So really quite similar to the last problem. A lot more stuff to put underneath the root. But what are the two main things I'd like you to notice from this problem that's different is the fact that when you have an odd root, if there's a negative inside, you can just take it out. And the other thing I want you to take note of is this is a cube root. So we're looking for groups of 3. You can have all different kinds of roots. You could have 4th roots, 5th roots, 6th roots, etc. All right, let's go ahead and move on to another one. So this is multiplying square roots. Multiplying square roots is a lot like just simplifying them. So the first thing that you would want to do is break them down. Multiplication symbol there. And when you multiply square roots, numbers that are on the outside, like the 2 and the -1, we're going to go ahead and multiply those together. So 2 times -1 is -2. And then the numbers on the inside, you can put all those together also. Now I'm not going to multiply them together though. The reason why is because when you're doing square roots, you want things broken apart so you can find your pairs, right? So I've got a pair of v's here, so I can take a v out. I've got another pair of v's right here, so I can take another v out. And then I have a pair of 3's here, so I could take a 3 out. And the 5 has no pairs, so that 5 stays under the root. So on the outside here, we have those 4 numbers that we need to multiply together. So that's going to end up being -6v squared, square root of 5. So the trick here that you want to take note of is that when you're multiplying, outside numbers get multiplied together, inside numbers get multiplied together, and then of course we break apart the inside, take out the roots. Here's another one. So you're noticing here that we have 4th roots. So let's go ahead and take a look at this. Now in this case, they're all inside numbers. There's no numbers outside of the radical. So we have 25m. Now if you break that apart, you end up with 5 times 5 for the 25. And we have 5 m's. And then we also have the 50m here, which is 50 is 25 times 2. 2 times 5 times 5. And then another m. And we're dealing with the 4th root. And I was a little bit wrong. You could say there's a 1 here and a -1 here. So we could say that there is some outside numbers if you want to say that. 1 times -1 would be -1. So there's still a negative out there. All right, so notice my root this time. It's a 4th root. So we're looking for groups of 4. So I've got 4 5's here, right? And so every time you have a group of 4 that match, you could cross off the group of 4 and put one of those numbers on the outside. So 5 on the outside. I also have 1, 2, 3, 4 m's right there. So I can put it m on the outside as well. And I don't see any other groups of 4. So on the inside we still have an m, a 2, and another m. And so if we just simplify this, on the outside, -1 times 5 times m is going to be -5m. And on the inside we have 2m squared. And we don't want to forget that little number right there. The radical index is 4. So we are answer there. Okay, let's go ahead and take a look at another problem. So on this one, we're dividing square roots. When you're dividing square roots, the first thing you want to do is break them down first. So we have 5 times 3, and we have 3 times 2. Now, whenever you have, when you're dividing two square roots, if they're both square roots, it's okay to reduce. So like I can take the 3 off because both of those numbers are square root 3's, so they can cancel. Just as a heads up, really quick, let's say we had this. Let's say I had a 2 on the outside. You could not do this because this 2 is under the root and this one's not. Okay, so just so you guys are aware of that fact. But in this case, since both of these 3's are under the root, they do reduce. Okay, so what that leaves me then with is the following. Now, one final thing, we don't like to have square roots on the bottom of fractions. So what we do is we do something called rationalizing. Process we go through to get the square root off of the bottom. What we do is we multiply the square root on the bottom by itself. So I'm going to multiply the bottom by the square root. And whatever you do to the bottom, you have to do to the top also. On the top, since both of those are square roots, I can put those together to get 10. I went ahead and multiplied them because both of these are prime. I can't break them down. So if I put them together, I'm still not going to have any pairs. So I might as well just multiply. Now in this case, the long way to go about it is to say, okay, well the square root of 2 times the square root of 2 is the square root of 4, and then that's 2. The other way is anytime you multiply a square root by itself, you just get the number. And there's our final answer. Okay? So that is how you rationalize square roots. So on this one, we're just being asked to simplify. Now you'll notice that this time we have a negative on the inside, but it's not a cube root like it was on number 2. This is a square root. Now whenever you have a negative underneath of a square root, there's no real answer for that. It's impossible to take the square root of a negative number. It's possible to take the cube root of a negative number, but it's not possible to take the square root of a negative number. So what we do is we're still going to take the negative out, but when we do, we're not going to put a negative on the outside like we did on number 2, but instead we're going to put an I on the outside, so it looks like this. Okay. After that, we're going to handle this part like we have been. So we're going to break it apart, right? 9 times 8, 3 times 3, 2, 2, 2. So now since we're dealing with square roots, we're looking for groups of 2. So there's a group of 2. And there's another group of 2. And so I'm left with 2 times 3 times 7 on the outside. That's negative 42. And then there's the I still, of course. And there's 2 on the inside. And there's our final answer, the number 6. So thing to pay attention to here is that if you have a square root with a negative on the inside, we're going to take that negative out. We're going to put an I on the outside. All right. Now, these are called complex numbers. A complex number is whenever you have a normal number, a real number, being added to an imaginary number. Okay? In this case, we're being asked to add two complex numbers together. Whenever you do that, basically you just need to combine the parts that match. So I'm going to combine the real numbers together, -1 and 6, that makes 5. And then in this case, 7i and -2i, combine those and we're going to get 5i. There's your final answer. It's a lot like combining like terms when you're just working with polynomials. Here's another example, but this one's subtraction. Notice there's a subtraction sign in the middle. Since that's there, what we're going to do is we're going to distribute the negative into the second set of parentheses there. So if we do that, the 5 becomes -5 and the I becomes minus I. So we have, now we're just going to treat this problem like we did in the last one. We're going to combine the like terms. 1 and -5 makes -4. Negative I makes -2i. On this particular problem, notice there's no sign in between. We're going to be multiplying these. And once again, we're going to handle this a lot like we did whenever we were working with polynomials. So we're going to make a box. And we're going to multiply to fill in the box. So 1 times 4 is 4. 1 times 5i is 5i. 5i times 4 is 20i. And then 5i times 5i is 25i squared. Then we're going to go ahead and take these four numbers out. Box. And any like terms that we have, we're going to go ahead and combine. So we can put those together, right? I think I made a boo-boo there. We're going to combine our like terms there. 25i. Now at this point, we have something else to be aware of here is this. So I is what we have whenever there's a square root underneath of a negative, right? I'm sorry, a negative underneath of a square root. I is the square root of -1. I squared, well, if you square both sides of this expression up here, the root cancels and you're left with -1. So I squared equals -1. So I'm going to replace this I squared here with a -1. (25) times -1 is -25. And so if I combine the 4 with the -25, there I end up with -21. So when you're multiplying complex numbers, anytime you end up with an I squared, it's going to become a real number, -1. Moving on to number 10. In this case, they want us to simplify this. So first of all, the negatives just cancel, right? That's pretty simple. Use just like you normally would. However, in this case, remember, I equals the square root of -1, right? So since I is equal to the square root of 1, that means we have a square root in the bottom. And if you remember what we talked about on an earlier problem, you're not supposed to have square roots on the bottom. And what we did to solve that problem was you multiply the square root by itself. So I'm going to multiply the bottom by I. And whatever you do to the bottom, you also do to the top. Now I've got 8i on the top. And on the bottom, I've got 7i squared. And what we talked about on the last problem is that I squared equals a -1. So I can replace this with a -1. And when I multiply 7 times -1, I'm going to end up with -7 on the bottom. And usually when you have a fraction and there's a negative on the top or bottom, we just kind of put it in front of the whole fraction. It makes the entire number come out negative. Let's move on here. Number 11. Now this problem is different than number 10 because instead of just having an I in the an imaginary number in the bottom, it has a complex number in the bottom. We have a real number being combined with an imaginary number. The way that you are going to deal with this is going to be a little bit different than number 10. What's similar about this problem number 10 is that we don't like having the I in the bottom. But you're not going to be able to just multiply the bottom and the top by I. If you did, when you multiply here, you're going to get I squared and it's going to cancel out the I, right? But since you're multiplying the entire bottom by I, you also have to multiply this by I. And so even though the I will cancel here, you're just going to end up with another one over here, and we haven't solved our problem of actually getting the I at the bottom. So there's another way to handle these, and tricky mathematicians kind of notice something kind of cool. If you multiply this bottom by itself, but with an opposite sign in the middle, everything kind of turns out hunky-dory. So when you have an I in the bottom, or a square root, regardless of whether it's I or normal square root, if you want to get rid of the square root off the bottom, then you're going to multiply it by the same expression, but with a plus in the middle instead of a minus, or vice versa. And this is what we call a conjugate pair. Conjugate pairs are kind of like binomials. Two pairs of binomials that are the same except for the sign in the middle is opposite. Okay? So that's how you deal with that. So, but don't forget, whatever you do to the bottom, you have to do the top also. Okay, so I'm going to multiply the top and bottom of this fraction by the conjugate pair. Right. Now on the top, that's pretty easy. All we have to do is distribute. So let's start there. I'm going to multiply the 7 into that binomial on the top. That's going to give me 42 plus 49i. Now on the bottom, though, we have to multiply two binomials together. So like a problem that we did earlier today on this lesson is you're going to use the box method. Now something that we should be noticing here as we're working on this, you guys, oops, too far. Something that we should be noticing as we're working on this, that the goal of this is, remember, is to get the square root out of the bottom. So let's watch how that happens. Here's one thing that kind of makes the I go away. Notice how these are the same number but opposite signs. So they cancel out when you combine. So all I'm left with then is this. But we also talked about how I squared is actually not even an imaginary number anymore. I squared is actually just a normal -1. So now we have 36, double negatives makes a positive 49, and we can add those together. That's going to be 15, that means 85. So notice that there's no more I on the bottom. So when you multiply a complex number by its conjugate, you end up with a real number with no imaginary part to it anymore. So that's the big aha there. Now sometimes you might need to reduce these things afterwards though. It's possible if you can find a number that goes into all three coefficients, then you can reduce it. So is there anything that divides into 42, 49, and 85? I think 7 does. Let's see. 7 goes into 42 6 times. 7 goes into 49 7 times. And I think it goes into 85 also. Let's see. 7 goes into 85. No, I don't. Maybe it doesn't actually. Pretty sure now it does not actually. So, no. Okay. Never mind. But what you do want to do is try to reduce it if possible. In this case, there's no common factors. You can't divide something into all three of these. We're done. Let's continue. Here's another problem. It's really just a repeat, but there's a little bit of a difference here. So we want to multiply. We don't like the bottom having an I in it, right? So we need to multiply by the conjugate of this bottom's -7 plus 3i. And whatever you do to the bottom, you do to the top. I need to multiply the top by that as well. Okay. So at this point, we have to do the box method twice. So I have to do it for the bottom and for the top. So that's really the only thing that's different about this problem is comparing it to number 11. On number 11, we just had a single number up here, so we just had to distribute it. But in this case, we have binomials in the top and bottom. Or I shouldn't be calling these binomials. Like binomials, but these are complex numbers. So we have that situation on the top and bottom. So we actually have to do the box method for both of them. So let's do the top first. 1 plus 9i is being multiplied with -7 and 3. I'm going to be showing a little bit less work because of my space constraints here. But if you simplify this, -63 and +3 come out to make -60i for the imaginary part. Now this down here, this I squared is going to make the 27 a negative. So -27 with -7 is going to make -34. So that will be the numerator. Now we'll do the denominator. And remember, our whole point in doing this exercise is to get the I out of the denominator. So when we're all done here, we shouldn't have any i's left. Well, that's a positive 21i. And this is a negative 21i. Squared. So these cancel like we would have expected. I squared is going to make the -9 become +9. So when I combine 49 with +9, I'm going to be ending up with 58. Now in this case, we do have something we could divide out of all three of those numbers. They're all even, right? So I know I can reduce by 2 at least. So let's do that. 2 goes into 34 17 times. 2 goes into 60 30 times. It goes into 58 26 times. Nah, nothing else reduces out, so we're good to go. Right. Next thing we're going to look at is solving quadratic equations. So quadratic functions, you guys, are functions where the x variable or the input variable is squared. This is what we call standard form. Matter of fact, standard form of a quadratic equation. There's another form which we'll talk about next week in our next lesson called vertex form. But this week we're focusing just on standard form. Now, for standard form, if you ever let the y equal 0, what does that do for you? Well, what we're going to do is we're going to plug 0 in for y and we're going to solve for x. Now, what does that accomplish for us? Well, thinking about it in terms of a graph, when y equals 0, that means you're on the x-axis. So Whenever you solve a quadratic equation that's set equal to 0, what you're doing is you're finding where that quadratic equation touches the x-axis. Now, quadratic equations usually come out to look like U-shaped. Well, actually, they always come out to look like U-shaped. So, called parabolas. So, for the next 4 or so problems, we're going to be solving quadratic equations. So I've got a quadratic equation here in standard form, and notice how in this case it's equal to 0. So there's a couple ways you can handle that. One way to handle it is with factoring, but the method that I'm going to be using for the next 4 problems is I'm just going to be using the quadratic formula. So how do you solve quadratic equations that are equal to 0? Very important that it equals 0. If it doesn't equal 0, you can't do this. But basically what it is you're going to use the quadratic formula. And that will tell you what x equals. If you're trying to solve for x on a quadratic equation that equals 0, you can solve for x using this formula called the quadratic formula. Okay? So I'm going to be using that. Now the number in front of the square is the a. The number in front of the non-squared variable is the b. And the number without a variable is the c. Okay, so all we do is plug in the numbers and go to town, work it out. All right, so let's give it a shot. So since it equals 0, I can solve for v using the quadratic formula. I'm going to replace all those letters with parentheses. B goes in the first 2 blanks, so my b is -4. Common mistake I see a lot of students is they put the variable in there too. You don't. You just put the coefficient, the number only. The next spot is the a number, which is 1, and that's going to go on the top and the bottom. And the last number we plug in is the c, which is so basically what we're dealing with here now is just knowing how to do order of operations. So I'm going to simplify underneath of the square root here mainly in the beginning, but we can also take care of these too. So let's go ahead and take care of these 4 groups here. They're all multiplication problems. Double negatives on the first part there makes that become a +4. -4 squared is 16. And if I multiply those 3 numbers in the box there together, I get 28. And on the bottom, I have 2 times 1, which is 2. We can continue simplifying underneath the square root by subtraction there. It's going to end up giving me 4x equals first. 16 take away 28. That 12, I think, -12. Okay. Sometimes at this point, you're all done. If you can't simplify your square root anymore, then you would stop. But in this case, I actually can. I can keep going. First of all, there's a negative underneath of a square root, which, as you guys know, we talked about earlier in this lesson. You take the negative out and you put an I on the outside. Now, what that means then, remember, this process is how you find where this equation touches the x-axis. If you have an imaginary root, an imaginary x-intercept, that means there is no x-intercept. If you were to graph this function, it actually doesn't touch the x-axis at all. But we're going to go ahead and still simplify this expression. So now, in this case, we can still simplify this square root some more. 12 is 2 times 2 times 3. You break it down using the root method we talked about earlier. And we can take a 2 out, as you can see. So, let me rewrite this a little bit cleaner then. And sometimes you're done there. You don't have to go any further. But in this case, we're still not done. We still have a little bit more to do. Just like we did with complex numbers, if your three coefficient numbers have something in common, then you can reduce it out. But remember, it has to be all three. It can't just be two of them. So since all three of those can be divided by 2, then this is what you'd have. Now, in the case of this problem here, if your denominator is ever 1, you really don't need to write the denominator. And we also don't need a 1 as a coefficient. So this is what the answer would look like. We're going to do a couple more of these, and all of them have a little bit of a different twist that happens as you go along solving it. Take a look at another one. Okay, let's take a look at a second quadratic formula example here. So my A is 1, my B is 9, my C is negative 13. Okay, so let's go ahead and plug in the B in the first two spots. The A goes in the next spot as well as on the bottom, and the C goes in. So that becomes negative 9. That becomes 81. That becomes negative 52. So notice I've got a negative 52, but there's also a minus sign there, so those double negatives are going to become positive. And then we have a 2 on the bottom, right? Next, we're going to go ahead and add those together. Let's see, that's going to be 133. Now 133, the next thing we would do is try to break down the square root. Last time we had a negative on the inside here, but we don't, so we're not going to take out an I. But we do need to try to break down the root. Now I'm pretty sure that's if it's not a prime number, then I'm pretty sure it's not going to have anything in it that makes a nice square root. So at this point, I would just check my multiple choice answers and see if that answer is one of them, and it is. And you'll notice that they write it as two separate ones, one with a plus and one with a minus, instead of writing it as one thing with a plus and a minus. But either way, it's fine. All right, so that one is an example of a problem where the square root doesn't simplify, so it actually makes it a little bit easier. You just stop right there. Let's take a look at another one. Let's see what happens with this one that's a little bit unique. So we have our A is 3, B is negative 7, and C is negative 98. B goes in the first two spots, A goes in the next spot and on the bottom, and C goes in the last spot. Alright, so double negatives there makes that a positive 7. When you square a number, it becomes positive, so that's a positive 49. Ooh, that's a pretty big number. That's no fun. Let me get my calculator out here. Alright, 4 times 3 times negative 98 gives me negative 1,176. Ew. Rotor. And then the bottom, of course, is 6. Okay. In this case, we have double negatives can become positive, and then we're going to add these two numbers together. So let's do that. It's not negative anymore because of the double negative. So we're going to do 1,176 plus 49. And that's going to be 1,225. All right. Well, that's a really big number. But let's see if we can break it down a little bit. Now, I know that 25 will go in there. You might have recognized that 5 goes in there. It doesn't really matter where you start, just so long as you know that something goes in there. But 1,225 divided by 25 is 49. All right, so that's 25 and 49. And then 25 is 5 times 5, and 49 is 7 times 7. So since we're taking a square root of this, the square root of 1,225 is the square root of 5 times 5 times 7 times 7. And you can take out a 5, and you can take out a 7. Putting those together, we get 35. So that square root simplifies to just 35. So what makes this problem special is that once you take the square root, there is no more square root. That's a perfect square root. The square root of 1,225 is just 35. We took all the numbers out. There was nothing left under the square root. When that happens, your answer is not a square root anymore. We just have a nice, normal, rational number is what we call it. So make some more space for myself. Now, that's what makes this problem special, and that's why I included it. Now, when that happens, you're actually going to do something a little bit different than usual. What you're going to do is you're going to split it up into two problems. One where it's plus, and one where it's minus. And then you're just going to simplify those two fractions separately. So on the top, 7 plus 35 is 42, I believe. And if you divide that by 6, you end up with 7. So there's one of my answers. The bottom one here, if I do 7 take away 35, I end up with negative 28, I believe. And then if we reduce that fraction, I'm going to end up with negative 14 over 3. Okay, so when you have the situation where the square root is a perfect square root, you can split it up and actually simplify it until you end up with just two basic fraction answers. Okay. So that's that one. And then there was one more example I wanted to show you. You'll notice the difference about this one is that it doesn't equal 0. And that's important because remember I told you the quadratic formula only works when it equals 0. So we can fix that. We can make it equal 0. Here's what you would do. In this case, we want to take everything off of the right side here. If I subtract 12a squared on that side, I'm going to subtract 12a squared on this side. And as I do that, I'm going to line up the terms that can actually be combined. So I can put my a squareds together there. And that's going to leave 19 take away 12 leaves me with 7a squared. And then we also have a 6 that I could bring over. So I need to drop that 6 off. And the 6 will combine with the 10 because those are just both normal numbers. So the 8a, you'll notice, doesn't combine with anything. That one's just going to come down as is. But 10 take away 6 leaves me with 4. And now it does equal 0. So if you ever have one where it doesn't equal 0, just move everything over to one side and combine your like terms and make sure you put it in descending order, highest power to lowest power. And then from there, you can just go ahead and do the quadratic formula. After this, nothing much interesting is going to happen. That was the main thing I wanted to show you for this problem. But if you want to see one more example worked out of the quadratic formula, go ahead. If you feel like you got it, there's really no new twists and turns at this point. You can probably just fast forward through at this point. So, but I will work it out in case you do want to see it. All right, so B goes in the first two spots, A goes in the next spot, and on the bottom, C goes in the last spot. And simplifying all this good stuff, we're left with -8 plus or minus 64 minus, I do not know what that is, 4 times 7 times 4, so let me work that out real quick. 112. Okay, and now we're going to go ahead and subtract these two numbers here. So we want to do 64 take away 112. And I'm getting -48 for that. Now this thing here can be simplified a little bit, so that's our next task. We want to simplify that square root of 48, -48 I should say. So first of all, we take the negative out and we put an I in the front. The next thing we do is we break it down. Now 48 is 16 times 3, and 16 is 2 times 2 times 2 times 2. Now if you can just do a factor tree like we've been doing on the other problems. You got to do that, but that's so I could take out a 2, and I could take out another 2. Gives me a 4i radical 3. Okay, so that means this square root of 48, I'm going to replace that with 4i root 3. Now we can reduce the 3 coefficients by 2. And there's our final answer. Okay. All right, moving on. At this point, we are going to talk about solving quadratics again, but this time we're not going to use the quadratic equation. You could, but the directions tell us solve it by taking square roots. So here's what they mean by that. What makes these problems special is that they're not written like this. For these, you really do need the quadratic formula, or you can do factoring sometimes. But this one's different. It looks like this. When you have just an x squared and you don't have the middle x number there, you can solve this just doing some basic algebra instead of doing the quadratic formula. So I'll show you what I mean by that. Just get the x by itself. Step 1 is to add the constant number to the other side. Step 2, if there's a coefficient, divide it out. Step 3, take a square root. However, you have to be careful when you use this method that if you use this strategy, you remember that after you take a square root, you always get two answers, a plus and a minus. The reason for that is because this is what we had, right? There are two numbers that when you square it give you 81, and the answers are 9 and -9. So the square root will tell you what the number is, but you have to remember that it is positive and -9. So we have two answers. Okay? We'll do another one like that, but the next one's a little bit harder, so let's take a look at this one. All right, so minus the 8 on both sides, and you get -18. Divide by 10 on both sides, and you get -18 over 10. Now that reduces. You divide the top and bottom by 2, you get this. Okay? And now we're going to go ahead and take the square root on both sides. So, square root cancels out the square. Don't forget you get a plus and a minus. But you'll notice that we have a little bit of a situation here. This can be simplified sometimes. Sometimes it can, sometimes it can't. So first of all, notice that there's a negative under square root. So we're going to go ahead and take that out and put an I in the front. The next thing I want you guys to be aware of is that when you're taking the square root of a fraction, basically you're taking the square root of the top and the bottom separately. Okay, so square root of 9 is nice. We know that. That's 3. But 5 does not have a nice square root, so we're just going to leave it as the square root of 5. But you remember from earlier in our worksheet that we don't like square roots on the bottom. So I'm going to multiply the top and the bottom by the square root of 5 to simplify. And so we end up with 3 square root of 5 on the top and 5 on the bottom. A lot of times, I think when they have answers written like this, they'll put the I back here instead. But it doesn't really matter where it goes. So this one's a little bit harder because we ended up with a fraction. So, reduce if you can. Same rule about taking out negatives applies. But the main thing to pay attention to here is that when you take the square root of a fraction, it's like you're taking the square root of the top and bottom separately. And don't forget to get the square roots off the bottom. Okay, so let's move on to number 19 and then 20. I may not do 2 problems. Yeah, I guess I will. I'll do 2. It's kind of repetitive, but so next week we're going to talk about graphing quadratics in vertex form, but this week we're talking about graphing them in standard form. So how to graph in standard form is kind of a series of steps to go through when you want to graph a quadratic in standard form. Okay, so step 1 is really what we want to do is we want to find our vertex. Now to do that, there's a 2-step process. The first thing is you want to find the h and the k, right? That's our goal. That's what I'll call the vertex h comma k. Find your h. The h value is negative b over 2a. And then to find your k value, k is what you get when you plug your h value into your equation. So after we solve for h here, we're going to take that answer and plug it into our equation to find out what the y value is. So y of h equals k. Once you have that, you could get kind of detailed and be very specific if you want to. A lot of times what you'll do is you can graph the y-intercept. That's easy to do. The y-intercept is next. Let's do that. Y-intercept is 0, comma c. So whatever this number is over here, that's your y-intercept. And then finally after that, you just go ahead and draw your parabola. This part could be a little bit tricky though. So I'll show you what I mean when we get there. But there's our steps. So let's go ahead and go through the process here and graph this parabola real quick. So first step is I want to find my vertex. So I'm going to start off with finding h equals negative b over 2. So my b is 16, my a is 2. Okay, so that means that h is going to be negative 16 over 4, which reduces to negative 4. I've got my h taken care of. Now I want to come over here and I want to find out what the k value is. So to find the k value, I take this answer for h and I plug it in for x over here in my equation. So I want to plug in the h value into my function. All right. So when you're doing this, you have to remember order of operations. You do your power first. So negative 4 to the second power is 16. Running out of space. And then we go ahead and do our multiplication. So that's 32. That's negative 64. If I combine these two together, 32 take away 64, that's negative 32. And negative 32 plus 4 is 2. So that's my y of 4. Or in other words, that's the k value. Okay, so now I know what my vertex is. My vertex is hk, right? So my vertex is HK. And I just found out that my H is -4 and my K was 2. Okay, so that tells me my vertex. So we're done with step 1. Step 2, we want to find our y-intercept. That's a lot easier. The y-intercept is 0, comma, and whatever the last number is 34. Okay, after that, you have enough information to kind of get a pretty decent graph of your parabola. So let me bring up my graph here a little bit. I don't like these pre-drawn graphs because then I can't draw it to the size I want, but that's okay. Let's go ahead and put our vertex on there first. So -4, 2, that's right about here. And then 0, 34, well, we can't even see that. So it's going to go way up here off the charts. 34 is way up here somewhere. So I'm just going to fudge it and say, okay, well, there's 34. So there's that. Now, what's important is we only have 2 dots, right? And you guys hopefully remember that the graph of a quadratic looks like a parabola. So it could be a happy face parabola or a sad face parabola. Now, this is the vertex, the part where it turns. Okay, the part where it's smooth and it turns the opposite direction. Now, which of these points was my vertex? Was it the one down here or was it the one up here? Well, the answer is it's the one down here. That's important to know because if you connect your dots like this, you're wrong because that way you made the 34 your vertex and it's not. 34 is actually your y-intercept. This is my vertex, so the only way to connect those dots rationally would be like that. So that's what my parabola would have to end up with. Okay, so we'll do one more example there. I'm going to clean up all the writing here, but if you want to take a picture or something or some notes of steps before I erase it, pause the video and do that. Won't be on the next problem. All right, let's go ahead and do one more example just to kind of drill it into our minds. So step 1, find your vertex. So part A, H is equal to -b over 2 times A. My B is -4. A is -1. You guys notice there's no number there. In that case, it's a 1, but it is negative. So H comes out to be -2. Part B, we want to find our K value. The K value is what you get whenever you take your answer from part A and plug it into the original equation. Up a little bit. All right, so we're plugging in -2. Powers first, right? When we do our multiplication, you can think of this as a -1. So -1 times 4 is -4. -4 times -2 is +8. And then subtracting from left to right, we get 4 minus 5, which is -1. So my vertex is going to be -2 for the H and -1 for the K. Okay, next step, we want to get our y-intercept. So that's always going to be 0, comma, and whatever the last number is. And now we're good to graph our parabola. So -2, -1 is right here, and that's my vertex, so I'll label it. And then 0, -5 is right here. So I need to have either a happy face or a sad face connecting those dots. I need this one to be the vertex. So the only way I can connect those dots in the proper way is if I have a sad face. which, by the way, you can also tell that it's an upside down parabola because anytime that front number is a negative, it makes your parabola go upside down. If it's a positive, then your parabola goes right side up. So that could help you also in getting the correct shape. All right? And that does it. So I think we've gotten you guys through another week of review. More to come.